The other big target for our technology has been quantifying greenhouse gas emissions from area sources. By area sources, I mean things like landfills or large lagoons associated with intensive animal feeding operations. Those are, and others of course, are tailings ponds up in the Fort McMurray area. Those large area sources are very dispersed. They're very heterogeneous in terms of emissions, and it's almost impossible to use traditional point emissions monitoring techniques in order to get a good, valid quantification of emissions from those sources. So by working with the US EPA in the United States and also with the British Geological Survey in the UK, we've adapted our technology for this sort of application. So shown here in this cartoon is an image of an area source with emissions of a particular gas, let's say methane or CO2. What we have implemented is a means of using a single open path laser device, as shown here, on a programmable scanner to send the same laser beam successively to a number of different reflector targets in order to measure the path integrated concentration in a number of different paths. By combining that information with meteorological, typically micrometeorological information, it's possible to create concentration profiles and calculate the flux of gas emissions from an area source. Done a number of different projects with landfills and other area sources. There are a number of different commercial algorithms that are used to take those path integrated concentrations and meteorological data and convert them into emission fluxes. Such algorithms are called radial plume mapping, backward Lagrangian stochastic technique. This is a technique that was actually developed at the University of Alberta by Dr. John Wilson and his co-workers, and enjoys a lot of application in agricultural applications. The radial plume mapping technique was developed by the University of Washington and is endorsed by the US EPA for area source emissions. And we have been working with a large international oil company in demonstrating the capability of a technique called remote gas flux mapping for enabling the pinpointing of leaks and the quantification of emissions from large oil and gas area sources, like, for example, tailings ponds and gas plants and such. This shows a typical configuration for monitoring emissions from lagoons with multiple paths set up around the lagoon. This slide here shows that we make a system that can fly on a helicopter or on ground-based vehicles for doing rapid surveys for either methane or CO2 monitoring. And this is an example of a survey of a landfill in Spain. What I wanted to show you is this slide here, which is a test that we did with the Alberta Research Council and our oil industry partner to demonstrate the capability of the RGM technique. The end result is that using the combination of multiple path measurements and the RGM algorithm, we were able to identify not just the source of a leak to within 5 meters, but we were able to determine the strength of that leak to within 5 or 10%. So we're currently involved in some additional testing of this technique. We're doing some tests this very month with this oil industry partner in Northern England, and hope to be able to commercialize this particular application within the next year or two. So final slide. We've been in business for 12 years or so, and we've limped along with anemic growth some years and spectacular the next, and then reverse growth the following. What do we need in order to meet our growth goals? Two different things. We need longer wavelength room temperature continuous wave lasers to access fundamental vibration rotation bands in the mid-infrared. We're currently working with weak absorption bands in the near-infrared. In order to access the really strong absorptions, we need to get into the mid-infrared, and that will enable us to not only access new gases, but get greater sensitivity for existing gases. The challenge are that in order to do that, in order to be able to get into the business of supplying lower value mass market products, we need to significantly reduce the packaged laser costs in order to enable these goals. Today, we pay between $1,500 and $7,500 for each of these individual lasers. In order to get into a business where we can sell devices for less than $10,000 or less than $5,000, we have to be able to get the laser cost down to $100 or so. And that is the driving force behind the project that we're currently working on with ACAMP and other industrial partners within the laser technology space in Canada. So thank you for listening. If you've got any questions, I'll be delighted to try and answer them.